All right, we're back talking about implicit differentiation. Specifically, we're going to talk about taking the second implicit derivative. So much like we talked about in section 2.6, where you can find the second, third, fourth, fifth, whatever derivative you want by simply repeating the differentiation process, you can also do that with the implicit differentiation process. Now, I'll be real with you. We're not going to go more than probably the second implicit derivative for purposes of this class, because that will allow us to do everything we need in for applications in the next chapter. But there's nothing prohibiting us from finding the third or fourth or fifth, whatever whatever the nth implicit derivative. But here we're going to do the second implicit derivative of these three examples. Now the first two aren't so bad. The third one, though, takes a little work. So let's take a look. So we know how to do the first implicit derivative, so let's just look at example A to start with, and let's go ahead and compute the first implicit derivative. So we have basically the equation of a circle, x squared plus y squared equals 4. Well, that's a circle with radius 2. So this is very similar to the example we worked at the start of this section, where we considered a circle of radius 5. So the implicit derivative, the first derivative that is, we take the derivative with respect to x of both sides of the implicit function, which of course then we can take the derivative of each term on the left individually. So that gives us the derivative of x squared with respect to x, of course, the derivative with respect to x of y squared. And we can go ahead and say that the right hand is 0 because the derivative of 4 with respect to x is certainly going to be 0. Okay? So now we take these individual derivatives on the left-hand side. Okay, well, there's no variable mismatch here on the first term, the first derivative. It's the derivative of x squared with respect to x. So just 2x. Now the second derivative, though, remember, there is a variable mismatch here. It's the derivative of x. The derivative of y squared with respect to x. So there's a variable mismatch, and so we have to apply the chain rule. Remember, we're assuming that y is some unknown differentiable function of x. So the derivative is going to be 2y times the derivative of the inside function, which is y prime, equals 0. Okay? And now we solve for y prime. There's only one y prime term, so it's pretty straightforward here. We're gonna subtract 2x from both sides, and so we get 2y prime equals negative 2x. And then to solve for y prime, we're going to divide both sides by 2y, and so we get y prime equals negative 2x over 2y, which of course we could say is equal to negative xy. So here is y prime for example A. Okay, but we want to find the second implicit derivative. Okay, so we repeat the differentiation process. Okay, so our starting point now is going to be y prime equals negative x over y. Okay, if you want to take the derivative, you take the derivative of the derivative. So y double prime is going to be the derivative with respect to x of our first derivative, negative x over y. Okay? Now, of course, this is a quotient, so we should apply the quotient rule. It's a pretty easy quotient. There's not much there. But remember, if we differentiate a y term, we have to give it special consideration. So let's see what we end up getting. Apply the quotient rule. So we take the derivative of the top function. Okay, we have that negative sign there. I'm gonna go ahead and put the negative sign out front, since that is a constant multiple. It's negative 1. It's a scalar multiple of negative 1. So I'll just put the negative sign out front there. Okay, that way we don't have to worry about where does the negative sign go when we're differentiating all the little parts. Okay, so now we're going to differentiate, let's see, the top function. So derivative of x with respect to x times the bottom function y. minus the derivative with respect to x of the bottom function y times the top function x over the bottom function squared. Okay. What else can we do here? Okay, we gotta simplify next. So we have to actually take those individual derivatives. So we have that y squared on the bottom. Now the whole thing was negative, so we can't lose that negative sign. The derivative of x with respect to x is just 1. So you have 1 times y on that top left-hand side, so just y. Minus, okay, the derivative of y with respect to x is 1 times y prime. So you get y prime times x. Okay. Now, here's the thing that we need to realize. And that's the second derivative, but it's not simplified yet. Why is it not simplified? Because it includes y prime. But we know what y prime is, so we can substitute the known expression for y prime. Therefore, we get a second derivative in terms of x and y only. So right now, my second derivative has x's in it, y's in it, and y prime, which is the first derivative. We want the second derivative to only have x's and y's in it, not y prime. But we know what y prime is, so we substitute. Okay, so we go over here. Let's see. So we know what y prime is, and so we can substitute. And so we get y minus, okay, y prime is negative x over y. So we substitute negative x over y times that x that was already there over y squared. Okay, so what do we get here? Well, okay, obviously now we have a compound fraction, which we don't really like. Here, I'll write it out in maybe a little bit better form. So y, okay, we have a double negative. We have a negative x over y times x. So that's going to be plus x squared over y squared. Okay. Now, here's the thing. It's a compound fraction. We don't like to leave our answers in compound fraction form. So what we do is actually it's pretty easy this time. Just multiply the top and the bottom both by y, because the only denominator is y. So if I multiply the top and the bottom by y, I'm multiplying by 1. So I'm not changing the value of this second derivative, but I'm changing the form of it. And so what happens here is if I distribute the y on the top, it's still all negative, and then I have what? If I think about parentheses here, it's y times y, so y squared, plus x squared over y times y just leaves me with x squared, and I've gotten rid of that small fraction on the numerator. And then on the denominator, we have y squared times y, so that is y cubed. So now I have the derivative in terms of x's and y only. Now there's one last simplification we can do, and it's just a nice thing to do. I mean, here I guess we have done enough as far as we have the derivative in terms of x and y only, but this one will make it look a lot nicer. And what can we do? We know what x squared plus y squared equals. Now this won't always happen when you're doing these second derivatives of implicit functions, but in this case it does. We know what x squared plus y squared equals. The original function tells us that x squared plus y squared is 4. So we can make one final simplification and say the numerator is equal to 4. Because that's x squared plus y squared is 4, according to the original implicit function. So the second derivative is negative 4 over y cubed. And there we are. Again, all we did was repeated differentiation. But it took several steps there because we had a quotient rule. We had to simplify a compound fraction. So there is a little bit of work there. But it's not terribly difficult, just a little tedious. Okay? So that's the second implicit derivative. B is kind of similar. It's fourth powers instead of it both being quadratic terms. So let's see how it plays out and if it's different, or how it all works out. Okay. So let's see here. We are going to differentiate both sides with respect to x. So x to the fourth plus y to the fourth equals the derivative with respect to x of 16. Okay, now of course we take the derivatives individually on that left-hand side. So the derivative with respect to x of x to the fourth plus the derivative with respect to x of y to the fourth equals, and again we can say that's 0 since that is the derivative of constant. By the way, you see now why it's so important to always use your notation properly, because here if you didn't say we're taking the derivative with respect to x, this d over dx, or the capital D with the subscript x, like I use a lot of times, if you weren't precise, you would not realize that you need to apply the chain rule when you differentiate a y term, a term involving y. So that's why notation is very important when you're doing implicit differentiation. It'll even be more important when we do an application of implicit differentiation here in the next video or two. We'll have multiple variables, and we'll be differentiating with respect to time, and so there's going to be lots of variable mismatches, and we'll have to apply the chain rule all the time in those situations. But we'll get to there soon enough. All right, so back to the problem at hand. The derivative of x to the fourth with respect to x is just 4x cubed, according to the power rule. Plus, okay, now we have the derivative of y to the fourth. Okay, so the chain rule says you take the derivative of the outside function. That gives us 4y to the third. But then we need to multiply by the derivative of the inside function being y. And of course, the derivative of y is y prime. Okay, equals 0. So this is very similar to the problem we just worked in example A. Now, if we want to solve for y prime, what we're going to do is we're going to subtract 4x cubed from both sides and get 4x cubed. Oh man, my 3 is not working out for me. Oh, I lost my 0. 4x cubed, and actually it's going to be negative 4x cubed because we're subtracting that from both sides. And then we're going to divide by 4y cubed. And that'll give us y prime. Now, of course, that simplifies just a little bit. Y prime, there's a 4 on the top and the bottom, so we get negative x cubed over y cubed. Okay, so there is y prime, the first derivative. Now, if you want the second derivative, we differentiate again. So y double prime equals the derivative with respect to x of negative x cubed over y cubed. Okay, so we're going to need to apply the quotient rule yet again. So let's see what we can come up with. According to the quotient rule, we take the derivative, and in fact, I'm going to do the same thing as I did last time. Since we have the whole quotient is negative, we can apply the constant multiple rule and just put a negative out in front of our quotient rule application. So we take the derivative of the top function, which is x cubed, and we multiply by the plain bottom function, and then we subtract off the derivative with respect to x of the bottom function times the plain top function over the bottom function squared. So y cubed squared. Okay. Let's see what happens next. We need to take these individual derivatives. Of course, the derivative of x cubed with respect to x is 3x squared times y cubed, that was already there, minus, okay, we have the derivative of y cubed. So we're using the chain rule here because there's a variable mismatch. We're taking the derivative of the outside function, the cubic function, and we get 3y squared. Well, that's the derivative of the outside function. Evaluate at the inside function. And the third part of the chain rule says to multiply by the derivative of the inside function, the derivative of y prime. And we multiply, don't forget, by that x cubed that was already there. Okay, over the denominator, which a y cubed squared, we multiply the exponents and get y to the 6th power. All right, now we're at that same point where we have a second derivative in terms of x, y, and the first derivative, y prime. But we know what the first derivative is equal to. It's equal to negative x cubed over y cubed. So we can substitute that in. And that looks like it's going to give us another compound fraction. Let's see, we have 3x squared y cubed minus 3y squared. I'm going to put the x cubed, move it over a little bit, so that we don't have a fraction in the middle of those terms, of those factors rather. So y squared x cubed times, okay, y prime, what's y prime? Y prime is negative x cubed over y cubed. Okay, over y to the 6th. All right, so we have now written our second derivative in terms of x and y only. Now we just need to simplify. Same issue as before. We have a compound fraction. So what about if I multiply the top and the bottom by what? The only denominator. The denominator of the smaller fraction on the numerator, y cubed. What if I multiply the top and the bottom by y cubed? So I'm multiplying by 1, essentially, because y cubed over y cubed is indeed 1. All right, so what's going to happen here? I'm gonna need to distribute on the numerator. On the denominator, you can just multiply y cubed times y to the 6th power. Easy peasy. On the numerator, though, it's going to take a little more work. So let's see. What's y to the 6th times y cubed? So when we multiply two power functions, we add the exponents. So we have what? Y to the 6th plus 3 power, so y to the 9th power. Now on the numerator, okay, we have, let's see, basically there's two terms. There's 3x squared y cubed, and then there's this other, lots of terms here that we are multiplying. But we're distributing y cubed over those two terms. So I need to multiply y cubed times this first grouping. Here I'll circle them in red. So here's the first grouping we're going to have to multiply, and then we're going to multiply y cubed by this second grouping. Okay? So let's go ahead and do that. Of course, there's a negative sign out front, and then we have 3x squared, but we're going to have y cubed times another y cubed. Again, when you multiply those power functions with the same base, you add the exponents. So 3 plus 3 being 6. So 3x squared y to the 6th minus. Okay, here's the thing. This is actually a fraction. It's negative 3y squared x cubed times negative x cubed over y cubed. We're multiplying by y cubed. So that's going to eliminate that denominator and leave us with, let's see. Well, first of all, okay, notice here I have a negative and a negative. I have a double negative. Here, I'll circle them. Double negative right there and right there. So that's going to mean that term turns positive. So I could say it's positive 3, okay, y squared. And now I have x cubed times x cubed. So that's going to be, again, two power functions multiplied together. We add the exponents. So that's x to the 3 plus 3 power, x to the 6th power. Okay, Now we took care of the denominators. We don't have a compound fraction anymore. What can we do here? Can we do any more simplification? I think we probably can of some sort. So I notice we have an x to the 6, a y to the 6, 3x squared, 3y squared. Okay, so we can, okay, what's the original function? The original function is what? X to the 4th, y to the 4th. So if I was going to try to take advantage of the known fact that x to the 4th plus y to the 4th is 16, well then I would need to see an x to the 4th plus y to the 4th somewhere. So I'm thinking to myself, can I make that happen? X to the 4th, y to the 4th? I don't know. Let's see here. I can certainly factor out a y squared, and we can divide out some common factors. That'll for sure work. Let's see here. But what I mean by that is, let's factor out y squared from the numerator. So if I factored out y squared, that would give me 3x squared y to the 4th plus 3, okay, I factored out a y squared, so x to the 6th over y to the 9th. Okay? And so now I can divide out y squared from the top and the bottom, which leaves me with negative. Okay, that's 3x squared y to the 4th plus 3x to the 6th over, okay, we canceled off y squared, so that's going to be y to the 7th power. Okay, now if I'm going to go any further than that, is there anything I can do here? Just factor out a 3, that would leave us with x squared, 3 times x squared y to the 4th, so x to the 6th. I think that's good enough for us. I mean, okay, you could factor out 3, but does that really matter? I mean, I don't think that really matters. So I'll leave it like that. I don't see anything else, evidently, right off the top of my head, so maybe I might be missing something. Sometimes, I like to be able to take advantage of the fact of that known fact that x to the 4th plus y to the 4th is 16, but there might be a way to do that. I'm not seeing it though right away. I mean, I do have an x to the 6th. I have a 3x squared to y to the 4th. But I don't see a way to do that immediately. But I might be missing something. Hopefully not, though. I'll cross my fingers that I haven't missed it. Now let's look at the last example. All right, this one will take a little more work because, well, it's got a sign in there and it's got x squared y, which is a product. So this is going to take a little more work. But it's not too bad. Again, as long as we follow the proper rules for implicit differentiation, we should be fine. Okay, so let's see. We're going to take the part C here. We're going to do the derivative with respect to x of both sides. Here, let me actually make sure we have enough room here. So the derivative of both sides with respect to x. So that's going to be sine x plus x squared y equals the derivative with respect to x of 10. Okay? And now, of course, the next step is to immediately take the derivative of all the individual terms. So we have the derivative with respect to x of sine plus the derivative with respect to x of x squared times y. And we can go ahead and call the right-hand side is 0 since the derivative of 10 is 0. Okay. We can go ahead and take the derivative of sine. The derivative of sine x with respect to x is just cosine x. So that's cosine x. Now, notice we have x squared y, so that is a product. We must apply the product rule. So we write the derivative with respect to x of the first term times the second term plain plus the derivative with respect to x of the second term times the first term plane equals 0. Taking those individual derivatives now, we have the cosine along for the ride. All right, the derivative of x squared with respect to x is just business as usual, 2x times the existing y, plus the derivative of y is 1 times the derivative of the inside function y, which is y prime. So y prime times the existing x squared equals 0. So the first derivative, no big deal, man. That's very, very comparable to questions, exercises we have worked previously. Now we do need to find, of course, solve for y prime. Now there's only one y prime term, so I'm going to subtract the other terms to the other side, and that's going to give us y prime times x squared equals, well, negative cosine x minus 2xy. Okay? And now to solve for y prime, we divide both sides by x squared. So y prime equals, in fact, I'm going to do the same thing I did on the previous problem. Since both of those terms are negative, I'm going to factor out a negative sign and say it's negative cosine x plus 2xy. Just, there's less negatives to worry about. Okay, of course, over x squared. Okay, now that's the first implicit derivative. If we want the second implicit derivative, we differentiate yet again. So y double prime is going to be the derivative with respect to x of the first derivative, which is negative cosine x plus 2xy over x squared. Okay, simple enough. Now, of course, this is a quotient and thus requires the quotient rule. So let's just get right with it. Equals. All right, there's a negative sign, and so we have a constant multiple of -1, just like the last problem. I am going to put that right there. In fact, let me move that that equal sign just so we are not going to lose that negative sign. Okay, so we're factoring out a -1, and then we're going to differentiate all the variable portions according to the quotient rule. So we take the derivative of the top function, which is a couple terms. So it's the derivative of cosine x plus 2xy times the plane bottom function x squared minus the derivative of the bottom function with respect to x, so the derivative of x squared, times the plane top function, again needs parentheses here because it's two terms, cosine x plus 2xy all over the bottom function squared. So x squared squared. Right, so let's see what we can come up with now. The derivative, oh, I left, and I almost messed up because I almost lost my negative sign. So the whole fraction is negative. The derivative of cosine is negative sine. So parentheses here, negative sine, because we're multiplying by that entire derivative. It's two terms here. Plus, okay, we have 2xy. That requires a product rule. So plus 2. Now I'm gonna factor out the 2. 2 is a constant multiple. Then apply the product rule. So that's the derivative of the first function, x, times the second function, y, plus the derivative of the second function, y, times the first function, x. There's two parentheses there to close. The parentheses around the product rule application and around the entire derivative times x squared. Oh, that made this numerator massive. minus, okay, the derivative of x squared with respect to x is just 2x times the existing cosine x plus 2xy. All right, x squared squared is x to the fourth equals a negative sign that I didn't forget this time. All right, let's see here. Okay, we have negative sine x plus 2 times. All right, the derivative of x with respect to x is 1. So 1 times y, just get y. Plus the derivative of y with respect to x is just y prime. So imagine you have an outside function is x to the first power with the inside function of y. So the derivative of a variable to the first power is just 1, but then so it's a constant. So you evaluate at y, you still just get that constant 1, but you have to multiply by the derivative of the inside function, y prime. So we get y prime times the x that was already there, times x squared, minus, I think I should probably go ahead and distribute this because I think it's eventually going to need to do that to simplify. So I might as well just distribute this top right hand portion. That's going to give us what? Negative 2x cosine x minus 2x, no, actually, sorry, minus 4, not 2, minus 4x squared y. Okay? Over x to the fourth. Now we're to that point where we have our derivative, second derivative that is, in terms of x's, y's, but there's a pesky y prime in there. So I need to substitute the known value for y prime so that I can have my derivative in terms of x and y only. So let's see here. Rewrite negative. The entire thing is negative. Now, should I do any distributing here? I'll do the first step of distributing here. Okay, so I have negative sine x. I'm going to distribute this 2. So it's 2 times y, so 2y, plus 2x times y prime. Now here's where I'm going to substitute. What is y prime? Y prime is up here. There's y prime. Okay, in fact, let me just box it off so I don't mess up when referring to it. Where we go? Y prime right here. Okay, so I need to substitute that in. That's going to be negative cosine x plus 2xy over x squared. All right, so I distributed that 2. I plugged in what we know y prime is, negative cosine x plus 2xy over x squared. Okay, that is all still times x squared. And then I have this minus 2x cosine x minus 4x squared y all over x to the fourth. Now notice I do indeed have a compound fraction at the time being. But I think that actually is going to resolve itself because look what I have going on here. I have this entire set of this big set of parentheses on the top left hand of this numerator. It's all multiplied by x squared. But my denominator, that one little fraction's denominator is x squared. So when I distribute, well, the x squareds will cancel out, and now I won't have a compound fraction. So that I actually don't have to do much except simplify. I don't have to actually do any of that strategic multiplying. because that denominator is just going to resolve itself. So I'm going to keep now simplifying because that I do have my derivative in terms of x and y only, but it is not simplified. So I need to work on simplification now. So let's see. If I multiply, so I have, notice I have these what should I do first? What if okay, so I have basically two distribution exercises I need to do here. I have 2x times the set of parentheses negative cosine x plus 2xy over x squared. Then I have x squared times the larger set of parentheses. I don't like to combine lots of steps at the same time. That's room for error and it confuses folks. So I guess I'll do the smaller set of parentheses to start with, which is the 2x. Oh, I didn't mean to do that. I meant to erase that. Equals sign because I almost forgot my negative sign. Okay, so what I'm going to do is negative sine x plus 2y plus, I'm going to distribute this 2x. So that's going to be, okay, I have 2x and both of those terms are negative. Oh, what happened there? I'm not sure what I just did. Okay. Both of those terms are negative because you have negative cosine x. There's a negative sign in front of the numerator. So it's going to be 2x times negative cosine x, which means we're going to get negative 2x cosine x. So minus 2x cosine x. And then we have 2x times negative 2xy. So that's what? Minus 4x squared y. Let's double check that. We have 2x times negative cosine x. Oh, you know what? I have to erase that because I didn't multiply by the appropriate denominator as well. Okay, sorry. The numerator was right, not the denominator. Okay, so it's going to be negative 2x cosine x over x squared. I forgot about that denominator. Minus, okay, that's going to be 4x squared y over x squared. And now that's all times x squared. So I've almost taken care of all of my distributive property. I got one more to go there. So we have, just to reiterate, we had 2x times negative cosine over x squared. Okay? And then we had 2x times negative 2xy over x squared, which gave us negative 4x squared y over x squared. Okay, minus 2x cosine x minus 4x squared y. Oh, that's a terrible 4 and a terrible y. Minus 4x squared y. All over x to the fourth. All right, now one more distributive property, then we'll just collect like terms and hopefully be done. So we have negative sine x plus 2y. Okay, now here's the thing. Oh, I didn't distribute. The whole point here is to distribute. So I have x squared over here, x squared times this entire set of parentheses. So that's going to give me negative x squared sine x plus 2x squared y. Now notice, if I'm going to multiply by x squared, notice that both of these denominators are x squared. So that's going to eliminate the denominators and just give me minus 2x cosine x minus 4x squared y. Minus 2x cosine x minus 4x squared y over x to the fourth. Now, do I have any common terms or like terms that I can combine? I think I do. Let's see. Let's get another color real fast. I have negative 4x squared y, negative 4x squared y, and positive 2x squared y. So I can combine all of those since they're all versions of x squared y. What I have negative 8 and positive 2, so that's going to be negative 6 of them. Here, I'll always go ahead and write that negative x squared sine x, okay, since there's no, that doesn't match up anything. But now I have what? Negative 6 x squared y. And then I have, look, the last two terms are negative 2x cosine x and negative 2x cosine x. So that, again, those are common, those are like terms. So there's negative 2 and negative 2. So that's what? Negative 4x cosine x over x to the fourth. Oh, what else can we do? Two things. Notice every term on the numerator is negative, and I have a negative sign up front. So I can basically multiply all the terms by negative 1, and that will, because they're all doubly negative. Also, so I'll just do that to start with. And there's one more thing we can do. So we have basically we're going to reverse all the signs. You know, this negative sign right here reverses all the signs on the numerator or the denominator. But I'm going to do the numerator here since that'll make them all positive. So that is going to give me positive x squared sine x plus 6x squared y plus 4x cosine x over x to the fourth. Now, last thing. Notice that there's an x, at least one x in each term on the numerator. So I can factor an x out and divide out one factor of x. So let's see here. If I factor out a single x from all terms on the numerator, that'll give me x sine x plus 6xy plus 4 cosine x over x cubed. Or sorry, x to the fourth. And now if I divide out that common factor of a single x, I get looks like my final answer, x sine x plus 6xy plus 4 cosine x. Now if I cancel out a single x, I get x cubed. Oh, let's see if I can get a cube that's a little better. X cubed. I think we have it. I think we finally have our simplified y double prime, the second derivative of y with respect to x. That took a lot of work. Okay. Calculus, not so bad. The reason calculus class is kind of rough sometimes is because of all of the algebra. That was a ton of algebra. The only calculus was when we applied a quotient rule one time, we applied a product rule one time, we took a couple derivatives. That was the easy part. But all the hard part was all of that algebra to simplify that second derivative. Okay? All right, so that's second implicit derivatives. Of course, if you wanted a third or fourth, well, then you'd have to differentiate again. And to be honest with you, I'm not going to do that right here. And we usually don't. I mean, obviously, the third derivative, like with example A, would be a breeze. But other ones, it gets really complicated. Not complicated, just tedious. Just tedious is all. So that's second implicit derivatives. Of course, If you have any questions, always feel free to reach out. We will continue on soon, so I'll catch you in the next video.